All right, so this was pretty interesting. These guys made other crypto wallets, and they ran a bug bounty, and they gave them people 24 hours. Can you guys hold it down a bit? Yeah, they made a 24-hour bug bounty, and then they declared the thing was unhackable because nobody hacked it in 24 hours. So that's what I've found with an awful lot of these crypto apps. These people who store cryptocurrency. John McAfee did this. He tried to sell an unhackable hardware wallet, which was just an Android phone with a couple of software changes, not very secure at all. This is it's, you know, everything involved with cryptocurrency is always a scam, and the hardware wallets are just another version of the many scams about. So now this is very interesting. We'll especially tomorrow night's class will be going through this in a lot of detail. There are a lot of cookies. The fundamental problem: HTTP was never stateful. So Netscape added the magic cookie, so you have some way to keep track of who you are, and this turned out to be a disaster. And one of the fundamental problems is your browser automatically sends that cookie without you knowing it, and it tries to guess whether it's appropriate to send the cookie or not. And the problem is it's often not sure whether it should be sending that cookie or not. So what Chrome is about to do is change to 3 types of cookies. So when you set a cookie, you're supposed to put it in a category. And so they're now going to have none, lax, or strict. And this is all about cross-origin requests. If I put a cookie, if I put a request on my website in an iframe or something that refers to another domain, or a link you click that goes to another domain, should I be allowed, by clicking on my website, for you to make a purchase in Amazon? That's a good question. Maybe that would be nice. Maybe you should really have to log into Amazon or make some click on the Amazon site to buy something from Amazon. So that's a cross-domain request where you go from my page over to there. And should you be sending the cookie over there or not? And the answer is now you can choose, but if you don't choose, Chrome is going to switch its default from none to lax. And what that's going to do is break a whole lot of websites that are assuming that cookies are sent to the other website and don't. And so that means people who use Chrome, including the latest version that supposedly came out yesterday, is apparently supposed to, in version 70, was supposed to come out. And so some sites will be broken. And that's how I found out about this. There are web developers saying I've been going nuts. So I tried to figure out why my site is broken, and then I found this explanation. This is why. So he has some demonstration sites and stuff, and I'm probably going to make this into a homework for 129S where you get to play with these cookies. The cookies have gotten much more complicated, and this is all very insecure because it's very easy to confuse your browser about where it is anyway. And everything in the browser is based on the same origin policy. It tries to know which domain I'm on and treat that domain differently than external domains. But the fact is you're not really on just one domain at a time anymore. And browsers haven't really gotten there. So anyway, yeah. Slack cookie table. No, I don't know anything about it. This is for Slack, the app?
Yeah, so yeah. Slack, it's pretty good on privacy. We just had out, but being a software company. But they actually have a cookie table that you can look at, and it tells you exactly what cookies they're using in what way. And they're really upfront about the way that they're using. There's opt-out links on there too.
Well, I think this is very good because I know I went one time. I was even going to go to DEF CON and give a talk about this. Amazon has so many cookies, and some of them, some of them are secure and some of them aren't, and it's very confusing. Anyway, that's a good thing. Let me save this one in my news links. That's a good thing to know. Good. I may refer to that. And we may play with this because there's a lot of cookies of different types. And it is very confusing to everybody, including developers and end users. And the different browsers handle them differently until everybody is pretty lost. And I did this like 6 years ago. I did something where you could steal cookies and reuse them to get in people's websites. There's just a lot of problems with this cookie-based authentication. It's a complicated, confusing, insecure patch on a stateless protocol to try to make it stateful. So the Iowa caucus was hilarious. I was cracking up last night. So they had the caucus, and then they couldn't get the results in because they're blaming the app. Apparently, they threw together an app without enough time to test it for people who didn't know what they were doing. And apparently, people who were tied to the Buttigieg campaign, which would seem like a bad move, although I haven't seen a very clear explanation of exactly how that connection worked. But anyway, the app didn't work. The precinct workers didn't know how to use it. They ran out of phone lines, so they couldn't phone in the results. Some people tried to drive in the results, and they refused to let them in. And so they couldn't get the answer. And they still don't know the answer from the precinct vote that was yesterday, which is pretty outrageous. But it looks like Buttigieg won, but they've only got 75% of the data. Anyway, they had an app, and this app apparently was a disaster, and everybody is all upset about it. One of the Buttigieg precinct captains or somebody actually tweeted a bunch of images of the form they're filling in. And the first thing I noticed is the form is very confusing. There are far too many numbers you're supposed to put in, including numbers that are calculated, and a bunch of them are crossed out and erased and left blank because it's too confusing to calculate. So if that's the data they had to send in, I'm sure a lot of it's wrong. So they've been spending a whole day trying to get the original. I think they took photographs of the room so you can count the people. They took the paper. They're trying to audit it all. It's like one of these manual recounts. You had to recount all the paper ballots because all the electronic reporting stuff didn't work. Anyway, so AT&T, I think, bought Time Warner, and they promised that they would not filter it, and that's totally what they're doing. They're now they're preventing Time Warner from streaming on Netflix and other services in order to make more money. And they, in order to avoid antitrust legislation, they got a merger approved by promising they would not do this. So we will see if that has the force of a court order and they can punish them for this. I would think probably not. They probably omitted to actually sign a court document making this a condition. So we'll see. This is Elizabeth Warren's big thing, is breaking up the tech giants, saying they're just monopolies and they're just tromping over everybody and we need to break them up. And we'll see if she wins. That'll probably happen. And it looks like Bernie might win. So if Bernie wins, I think something similar might happen. And here's some pictures of some more information about the Shadow app. So it looks like this. You put in your precinct ID, you log in, and then you send up data. And the app didn't work properly. It crashed on phones. It wouldn't install right. Even if it did go, you had to type in all this complicated stuff that people couldn't figure out. And so many people are getting very upset and saying, why did you switch to this app? And then they, without enough time to test it. So anyway, this one is interesting. This is a flaw that has been patched in WhatsApp. He found that he could alter the text of a reply with something like response splitting. He was able to inject code that would change the values of variables in JavaScript, so you will see a reply which in fact came from the person that sent the original message. You can send a message and include something which will then be sent out as the reply. So you can trick people into appearing to give a different reply than what they really did. And that, of course, he thought it was just a prank, but then he went back to it and found out there was an open redirect flaw, and he was able to use that open redirect to point to local files and do local file disclosure vulnerability. So he's able to refer to other files on the phone at the other end and on the computer at the other end. This is for Facebook's desktop client. Anyway, he talks about how he got here and gradually went through all these steps and improved it until he could fetch data from other URLs and even from the local host. So it's a good example of what you have to do to really improve these flaws and make them powerful enough that people will get excited. This one I thought was pretty good. The Qt library on Debian will load plugins and libraries, but it doesn't specify the path they come from. So you can trick it into loading them from the wrong path. And this is an old trick called a companion Trojan, where you put a file with the same name as a file used by an app in the wrong folder, typically the user's current home folder. And now you can run, it gives you code injection. So I can get you to download something with something like a drive-by download that goes in your home folder. And then when I run something with system privileges from a system folder, it loads code from your home folder and runs it in another context. That's a common way to get code injection. And I used to be the fun way to take over Windows XP machines, and they seem to patch it in Vista, so you couldn't do it that easily anymore. But Debian had this flaw. And here's F-Secure Internet Gatekeeper had a heap overflow. And just a straight up heap overflow, you could inject code and corrupt the heap just the way we're doing in CNIT 127. So it's good, clean fun. These old tricks come back over and over and over again. And here's another one, TeamViewer. Until about 6 or 8 years ago, everything you used would read the password and stick it in memory, and it would just persist in memory in plain text. I did this at Hope like 4 or 5 years ago. I demonstrated stealing passwords from Chrome from memory. You could log into Google and your password was just sitting there in memory, which is ridiculous because Microsoft published the cure for this in 2004. Visual Studio has a variable type that will automatically be erased as soon as you're done using it to prevent this, but developers just don't use it. But now a lot of them have used it. So TeamViewer doesn't store your password in memory unencrypted, but they did, instead of using some safe technique like whatever the appropriate vault is, they invented their own system with AES, and they used just a fixed static key that's always the same. And the key is in memory. So this guy explains how he found the key, and then he decrypted it and found the TeamViewer things in memory. So, you know, this is the same mistake everybody makes. They make some stupid custom encryption. You should use the system-provided vault. You should not make your own encryption. If you do, you will always be sorry. Anyway, all right, so I think that's enough of this stuff for now. Let me just talk about what's going to happen tonight. So we're going to finish up the chapter on Android, 6C, and there's another chapter on Android coming after. This is the first one, Android applications. And then I have a non-disclosure agreement to sign for people who wish to see an optional presentation in something that I cannot tell the world about just yet, which should be good, clean fun. And we will not record that or put that on YouTube. And that'll be about 7, might be a little earlier because this chapter is kind of fast. And then I'll be up in the lab to help people with projects. I know a great many people are having trouble connecting their emulator to the phone or to Kali. It's very painful, and it depends on your system. So it just takes a lot of hand help, personal help for a lot of people to get it to work. These emulators are very painful. That's why it's too bad the Genymotion Cloud cut their trial, because moving to the cloud would be the only reasonable solution. Every time I've taught this class and people have to use local machines, there was always great suffering because every machine is different. And all the apps run differently on different platforms. So it just takes a lot of struggle to get your things to connect. Using 2 physical machines is often the simplest way to do it. Anyway, so let's take a look at these slides about Android, which should be here. 6C, there it is. All right. So, we've been through the first 2 parts. Now we're down to the security model and reverse engineering, which we've already done last time. With the progressive app, and we're just talking about how it works. So if you want to secure an operating system, there are, of course, various ways to do it. Now, one thing you could do is actually write your apps more carefully, but that doesn't really protect all the apps. And of course, a great many people run old or poorly written apps. And you might wonder, is there some way to protect you even if you're running buggy apps? And there is. Those are called the generic mitigations. You can add security to the operating system, which helps prevent flaws even when you run an old app with a vulnerability. And so we'll talk about that, and then rooting and reverse engineering. So here's some common generic exploiting. These are things you do that affect the entire OS and they affect all the apps running on it. And you're trying to do something very difficult here. You're trying to add security to an app that was written without security, without breaking it. And that is difficult. And typically you push it as far as you can, and some older apps are broken. And but you try to push it, but you can improve the security of quite a few apps without the app knowing it's in a more secure environment. And in the most extreme case, you do something like put the app in a virtual machine on a more secure operating system, and then you have some improved security. Of course, there's a limit to how secure you can make it. And that's why everybody says you really should update to a more modern version of your app. But if you can't, or you won't, then they can do something to help protect you. So here's a series of limitations of these preventions. These all started in Linux and were ported to Windows, and Mac now has most of them too. The Mac is the last to adopt these because Mac had a much smaller malware problem, and they were, of course, much slower to add these things in. So stack cookies add a special random number to the end of each stack frame so that if a variable is overwritten and it tries to override all the variables on the stack and get to the return pointer, it will alter this cookie value, and your operating system will detect that and just stop the program. So you will not be able to use a standard aleph null type buffer overflow, which is what we're doing, of course, in the 127 class. We talk about this, and we'll be overcoming stack cookies as we go ahead. But stack cookies are one of the first, simplest mitigations, and they did stop the old classic buffer overflows. Then there's the safe IOP, which tries to deal with integer overflows. There are a lot of vulnerabilities you have to do with integer overflows. If you take the cryptography class, we go through the attack that was used to steal $1 million from the Ponzi coin, a cryptocurrency that was created, and they had an integer overflow. All you had to do was make an empty account and spend 1 coin from it, and it would roll under, and now you had a huge positive number because the negative number would just roll over and be interpreted as plus 100 trillion or something. So you had all the coins. And there are many, many examples of that. Another thing that's fairly common is you're trying to avoid making input too long. So what you do is you make it really long, like 50,000 characters, and that's interpreted as a negative number and therefore not long. Anyway, so DL Malik, we were just talking about heap overflows. There are many problems with heap pointers, and one common mistake is when you free the same chunk twice. You have a main routine that allocates some space, then you have a subroutine that uses it, and the subroutine frees it, and then the main program frees it also. Or the subroutine has an if clause that frees it, and somehow some other part of it frees it again. And if you free the same chunk twice, then you create a write under the control of the user. Then it takes data that was used for another purpose to assign these pointers. And we're playing with that in 127, similar problems at the heap. And so DL Malik was the original heap implementation, and there are extensions to make it safer. And then there's CALIC for integer overflows and format strings protections, which format strings are just amazing and entirely due to C. For some ridiculous reason, C, which is so strict about so many things, allows you to have a print statement without specifying the format. And if you do that, the attacker can inject a format string and they can totally take over the machine. And so they have a protection to try to prevent that. Then no execute, we've talked about a lot. This is putting permissions on RAM, and the Windows standard is you have to reserve memory for a program to run, and every memory segment has to be write or execute. You can either alter it or execute it, but never both at the same time. That's the Windows security model. If you could write and execute, then you could have self-modifying code. So anyway, it's enforced with this no execute bit. And the idea is wherever you're storing user data, you make it non-executable, and now no one can inject code and run that code. Any place where you can write cannot be executable, and so it stops, again, the classic buffer overflow attack. ASLR is another of the strong defenses. This means every time you load a program, you load it in a random location in memory. So programs don't know where they're going to be in memory, and that means that you don't know any of the addresses. So again, the classic buffer overflow where you inject an address that points back to code you injected is prevented because you can't tell the addresses of anything, so you can't find the code you've injected. And there are various ways to get around it. Of course, in order for that to happen, you have to compile your code with position-independent code, so it is all relative jumps. So it can be relocated and doesn't have to know where it is. If you don't compile, if you use old versions of GGC, or if you turn off this switch, you compile code that cannot be relocated, and then it's not compatible with address space layout randomization. RelRow is another way to make some areas read-only to protect them, to prevent things like global offset table injection. We're doing this a lot in 127. There are pointers to system routines in memory, and we overwrite them to take over the machine. And in retrospect, why do you allow people to change those pointers? They're just supposed to be pointing to system libraries. The user shouldn't really have the ability to change those. There's also ones in the kernel. There's a kernel table of jump pointers that we alter, and really, it doesn't make any sense to let the user change either of those, and this feature tries to prevent that. And there's another one here. This is essentially what Microsoft did. Microsoft, about 6 years ago, published what they did to improve C. All of Microsoft software is written in C or C++. It's very dangerous, but it's very fast. And they took a modification of the C libraries to remove about the 10 most dangerous libraries and force you to use safer versions. And they published all that so everybody else can use it. And that's the point here. Fortify source replaces most of the problems in C come from about 10 functions like string, copy, and getS, and a few others, things that read unlimited amounts of data into a string variable. Those are all too dangerous to use, and there are various library alterations that make it stronger. And then there's SE Linux. SE Linux was specifically designed to make security enhanced Linux to meet military specifications, to create a trusted computing environment to match the Orange Book. The Orange Book is I think came from the Navy originally. It is the military standard for security, and it defines a so-called thing called a trusted computing environment. And in order to meet that, you have to add a lot to the operating system, and all the operating systems, of course, scaled their product up to meet those standards in order to be able to sell to the military. So Microsoft added all these defenses into their system. That's why they added whole disk encryption and the trusted platform module. When the Windows is a cryptographic coprocessor on the motherboards of Windows machines since Vista, which is specifically named that to create a trusted platform to meet the military definition of the Orange Book of a trusted platform. And SE Linux was to do the same thing, to make it possible for these things to be secure enough. And it added a whole bunch of extra defenses to Linux. I keep running into it in modern versions of Ubuntu. Now, each app has its own restrictions on what it can do. So you have a whole other, like a firewall for apps. You have settings for what things each app is allowed to do and what folder it's allowed to get to, and it's another layer of protection. One similar defense added in Windows 10 to stop ransomware is their protected folders, where you can have a folder and say only one app is allowed to change the files in this folder, only Microsoft Word. So if ransomware tries to encrypt them, it can't, because only one app is allowed to go in that folder. And that's one of the many things that SE Linux allows you to have. Now, SE Linux has two modes. It's got a permissive mode where it doesn't block anything, but it creates a log. So you can see if an app is doing a bad thing, and then enforcing mode where it actually blocks you from doing things. And of course, the enforcing mode is more secure, but it will often break old software. And so you'll often spend time debugging software in enforcing mode. Then there's fortified source, another way to replace dangerous functions with stronger functions. And then there's kernel protection. This is a very common, generally the way you do privilege escalation is you find a SUID program. There are typically 10 or 15 of these files in a standard Linux install, programs that run as root even if you are not root. So all you have to do is run one of those and trick it into running extra code or crashing in as elevated state, and then you can escalate permissions. And so in Android, they actually got rid of them all in version 4.3. No more SUID, which is interesting. And I don't really know how they do things. Like if you change your password, you have to elevate to root to do that somehow. But I know they also do not store your passwords in the password file, not in Linux. They have some other system. So anyway, that's the thing to know. And then they removed SetUID from installed apps. So, you know, they removed all these dangerous SetUID files and used some other system for escalating to root, which I don't really understand. Anyway, and then so here's what rooting is, of course. If you are a normal user of a phone, you are not running as root. Although the first iPhone, everything did run as root, but there was no app store at that time, and Apple wrote all the software, and they thought it would be okay. But in modern phones, it is emphatically not okay. You're downloading third-party apps written by God knows who that have bugs in them, and you don't want to be running those things as root. Only the internal system processes run with high privileges. So when you root your Android phone, which you can do a variety of ways, then you add an SU binary, which gives you elevate to super user. And once you've done that, you can now do SU, and after that, you're root. SU has SUID permissions. This is what we were just talking about. By default, Android doesn't allow any of these files anymore. But if you root your phone, you add an SU binary to it, and this is RWS instead of RWX. And the S means when it executes with the permissions of the owner, which is root, and not the permissions of the person who launched it. So whatever you run with this program runs as root, even if you are not root. And that's a simple way to escalate. Now in Linux, every time you do a sudo, it will ask you for your password to verify that you have the authorization to do this. On a phone, it will pop up a thing like this. This is what's considered reasonably secure. Every time you do a super user, it'll pop up a thing saying, you really want to be super user? And if so, just for 15 minutes or something. That's the equivalent. You could also take that away and just execute everything as root with SU, but then there would be no protection from any kind of other malware or anything escalating to root. So this is what's considered a reasonable security balance for Android phones. So in order to root it, you either find an exploit, some kind of weakness in the operating system, and run a rooted program that will do it, or you reinstall the entire OS with a different bootloader. So there's just a whole series of exploits, and they're very much like any other Linux privilege escalation exploits. You find a defect in the Linux operating system that allows this. So this one used volume mounting volume daemon to write to the global offset table, and it could take it over. Older versions of Android. Then Samsung had this thing called Exynos, which had a bug in the driver you could use. The Admire had a similar bug, something to do with the logs you could use. And Iconia, this particular phone, had a pre-installed SUID binary that you could use with a code injection. Then there was the master key exploit we talked about before. You could have an app with two different sets of permissions. You could have two apps. And if you only had one set of permissions, it would only check the signature on the first set of permissions and then apply it to the whole app. So what you do here is now you pull a system app off, you add more code to it and put it back, and it will verify the signature is still valid for the first part. It'll run the second part with escalated privileges. So this is a fundamental problem. You're able to add code to something, but it still passes the signature test because of the master key vulnerability. And Chell root was a more advanced one later that exploited, I think, a race condition and locks, kind of like the dirty cow exploit on Linux. And that was a big one that rooted a lot of devices. And the other thing you can do is just run a different operating system. And this was very popular until about 5 years ago. Many people did this because the default Android OS was not very pretty and you couldn't put on a lot of apps. So a lot of people just replaced the OS with another. This is like people who buy a Mac and they put Linux on it. You know, you want total control of the machine. So you flash new firmware onto your Android device, and now you're running non-standard firmware that did not come from the developer of your device. And of course, you can do anything you want now. It's like running your own Linux install. You can put on any updates you want, any software, give yourself root privileges, and so on. Of course, this tends to void your warranty and such. And so there were just a whole lot of these things, from Clockwork Mod and many others. And the original reason these things became popular is you would have better wallpapers and more apps, and you could do forbidden things like tether to your phone and stuff. And a bunch of people would hack their Android to make it more powerful. And what happened is the default Android operating system got better. So it was really nice to use the default one. It had all those features anyway, and so very few people really wanted to do this anymore. This was all the rage 5 or 10 years ago, but most of the groups developing these things have gone out of money and gone broke because there isn't a large base of people that want to do this anymore. This one of the many. Paranoid Android was one of the big ones at one time, but in 2018, they finally gave up and said, you know, we ran out of money, nobody cares, you don't need this anymore, we're giving up. And there's probably still some custom mods out, bootloaders out there, but people aren't using them that much anymore. Anyway, and then there's reverse engineering applications, which we've already been doing in this class. So you can, if you put an app on the phone, you can pull it off the phone with ADB, and then you can unpack it with APK tool. You can see what's inside there, and then you can scan it for vulnerabilities. Now, you don't even have to unpack it with APK tool to scan it, because these scanners include an unpacker. So if you do the project, use Quark and AngroBugs. Both of these will find common flaws, and you will get used to an important thing about vulnerability scanners. Vulnerability scanners are very low quality, all of them. They miss important vulnerabilities, and they all have false positives. They will tell you there's a problem when there really is no problem. So whenever a vulnerability scanner tells you there's a problem, you have to go back and manually check, because frequently it tells you there's a problem, but when you look, it's not really a problem. It just means the scanner got some result from a probe that it didn't expect. But often it doesn't really mean that you can do anything. So JADX is very powerful, and we'll look at it a little later in the confidential section, but you used it in the projects in the Indian app. JADX gets you go all the way back to Java code. It's not, I think, perfect Java code, but anyway, you can read Java code. This is an entire app. This is from the Indian government app. And you can just see they've run this app through the default obfuscator ProGuard, which causes some of the routines to turn into A, B, C, and D to hide them, but a bunch of them are not hidden. And you have code here you can read. So here's the beginning of the app, and here's the launch routine here. So when you first start the app, it will run launcher. So if you're going to have a defense like this app has jailbreak detection and modification detection, and both of those are, of course, in the launcher, because it checks both of those things right away before it does anything else. And so you can look in the Android manifest file to find out exactly where the launcher is, and then you can just navigate to it in this tree structure directory and see the code for the launcher and see how it works and figure out how to modify it to take that off. And that's what we do in the project, is take away those protections from this Indian government app. And you can then modify here like we did. Simplest mod is just put in a couple lines to steal usernames and passwords and other things, secrets, and put them in the log. And once you do that, you can just repack the app, re-sign it with a different signature, and install it. And if the app doesn't have modification detection, which would be easy enough to have, it will run the modified version, connect to the server, and you could distribute it to people, and they would believe it was the real app. And it has the unexpected functionality that you added. So I've got some Cahoots about that, which should be ready to go here. This is 128.6C. All right. And that should do it. Sounds like I have sound and everything. And a place to put the winners. That's true. I guess their product is more popular, or they want you to think so. I see a chat message. I tried getting to class, but traffic is bad. Yeah, yep, that's fine. The extra part, I won't broadcast, but it's not essential. Should be fun for the people who could make it, though. I hope so. Yeah, that's the idea. Yeah, like the Easter egg. There's an extra thing which is only for the paid subscriber kind of thing. Yeah. No, it's not extra credit, but it's stuff where they have to sign an NDA to see it. And I'm showing you stuff that is not exactly public information. Okay. So I'll wait a few more seconds. All right, there ought to, all right, could be a lot more, but I guess this is all we're going to get. 5 more seconds. All right. Let's try these. So, what's the target of double free exploits? Okay, it's the heap. That's the point. Freeing the same thing twice on the heap creates a write condition which has parameters under the control of the attacker. All right, what does the NX bit do? Stack is the common target. It could be any memory region. It prevents the stack from being executable, so data you receive from the user, which is stored on the stack, cannot include executable code. That's the idea. Where do you put a canary value? All right, and that's also the stack. You put it at the end of every stack frame to see if somebody's been overflowing the stack. And I saw a chat message. I think this is for 120. No, it's not. The same thing was covered here. However, this totally is overlapping 127. You're quite correct. But it was in this class too. It could easily have been in 127. Yes. And what is the target of a format string attack? The print statements. Good. You're right, though. This particular lesson totally overlaps at 127. All right. So, the glorious winners. Rich, that's like a real name and everything. And Ken, that's another real name. And Kurtz, that's you, isn't it? Okay, good. Well, I think you might be out of the person that's always making fun of Kirk. I don't know. This is like outing you. All right. Anyway, so okay. Well then, okay. So I'm going to stop the Zoom recording, and I'll stop the Zoom share in a couple of minutes. This is it for the recording.